Well, good afternoon, morning, or evening to anyone who happens to be tuning in live, and for people who happen to be catching this offline on the podcast later on. Thanks for joining for what is now our 18th episode of Meet the meQuanics. I'm actually quite happy that this has kept going as long as it is. As I mentioned last week after our conversation with Andrea Morello from UNSW, today we've been honoured enough to be joined by Andrew Cross and Lev Bishop from IBM Research, who are another of sort of the private sector major players within quantum computing and quantum technology in general. So guys, thanks for giving me an hour of your time.
Yeah, our pleasure. And thanks for inviting us.
So obviously the main reason that I wanted to talk to you guys and why I sort of reached out to you is because of your recent release of the Quantum Experience. Obviously, disclosures in order. I have done some experiments with your platform and put out a paper. Hopefully that'll be published reasonably soon. But first of all, before we get into sort of what the Quantum Experience is and how you guys came up with the idea and you know what you're trying to get out of it, maybe give us a bit of a rundown of sort of the technology you're developing and where it sits. You guys are in the superconducting platform, so similar to Google, D-Wave, Rigetti, a few of other the major players. So basically give us a bit of a rundown of sort of how IBM got into this and why you guys are tackling superconducting quantum bits.
Would you like to? Yeah, so IBM has been in physics of information for a long time, since the 60s. And then as a kind of a natural development from that, we were there at the beginning of the quantum information ideas. And then in recent years, we've been focusing on actually building a quantum computer using superconducting qubits. So yeah, like several other players in the domain, we use transmon qubits. We are focused on fixed frequency transmon qubits at the moment, so we don't have any tunability in our system, although we're not married to that for the long term. But that's our current approach, and our general sort of short-term scaling approach is to build around surface code. So that's kind of the near-term goals, is to build small surface codes using fixed frequency transmon qubits.
Mm-hmm, mm-hmm. So, I mean, IBM's been in this space for quite a while now. Some of the pioneers of quantum computing have been based out of IBM. Obviously, people like Charlie Bennett, John Smolin, Sergey. The effort seems quite large. For those of us in the community, there's always sort of this question as to sort of that aspect of quantum computing that exists at IBM with the Bennetts and the Smolins and people like that. And then there's the experimental side with you guys and Jay and Andrew. How much is there sort of, do the two groups intimately work together, or are they sort of, two sides of the same coin?
Yeah, I mean, it's a pretty close team. We all talk to each other. I mean, there's obviously a spectrum from the people at the one end, working in the clean room doing fabrication. They don't have so much to say to Sergey about, coding theory and so on, but there's a whole spectrum, and there's discussions up and down the all across the board.
We're all pretty much co-located right now in the same place in the building. We talk to each other quite regularly. I think that's one of the things that's a bit unique about IBM, is that we do have a theory group. We have quite a large number of theorists working right now, and also a very large experimental effort. And we are working together, both thinking about applications of these small machines, as well as looking further down the road and thinking about what we'll need for the longer term.
So, I mean, Andrew, you're more on the theory side, and Lev, you're more on the experimental side, right?
I'm a theorist who's about as close to experiments as you can be and still call yourself a theorist without actually having to hand in your theory card. So I'm happy going in the lab and doing a calculation that says maybe one of your cables is 6 inches too long. That kind of theorist.
So sort of a device theorist more so than an information theorist.
Yeah, and I'm a theorist. I've been trying to spend some time spend a lot of time actually talking with experimentalists and trying to understand their issues. But I don't go into the lab. I don't make measurements. That's a good thing, and it really is for them. Yeah, so I think there's a lot of benefit by having a dialogue between these types of people, so that theorists really have a better understanding of what the real issues are and what the major obstacles are to building more coherent systems or larger systems. And then at the same time, I think there's benefit to share some of the ideas about applications and about error correction with experimentalists, that they have an idea of what we'll need in the coming years.
So, how much can you guys sort of give me sort of the background of how sort of IBM came into the superconducting sphere? Was it sort of just sort of by happenstance, or was this a concerted effort saying, no, we think this system's going to be the best, and therefore we're going to target this?
So, I think IBM's been working in this area for a long time, both with programs looking at classical computation with superconducting circuits, and also quantum computation. There's been work here for well more than 10 years in this area.
Itself. So before we really get sort of into this idea of what the quantum experience is and what you guys have put up, I just want to sort of get an idea of where your tech is, as much as you're allowed to tell me. So the quantum experience itself is a 5-qubit chip that we'll talk about in a second. But where are you guys where are you now in the lab? Are you able to tell me in terms of where your tech is, or where it's going to head in the next 6 or 7 months?
Yeah, so in the short term, we're moving towards larger numbers of qubits. We have a 7-qubit sample cold right now. There's obviously we're moving towards larger numbers of qubits in the teens rather than in the tens. But to make a useful computer, you really need a lot more. So there's one direction we're moving towards is more qubits. But at the same time, you need to work on coherence. It's not enough to have a lot of qubits. Your qubits need to be good. So in parallel, we have a whole separate program of just trying to make our single and 2-qubit gates as good as possible, try and reach the error correction threshold, and then maintain that kind of coherence while building out larger systems. So it's not good enough that you can do 1 and 2-qubit gates well in a 3-qubit system. You need to be able to do them just as well in a 10-qubit or a 50-qubit system, and that's the real challenge.
So where are your sort of error rates now in terms of sort of these fault-tolerant thresholds? So we all know that sort of you need error rates below about 1% for these systems to start working in the context of error correction. So in terms of your state-of-the-art, where are you now?
Yeah, so I think our best single-qubit error rate is at like 99.9, almost 99, 985, something like that. Our 2-qubit error rate is, 98 point something?
But the recent results were very, very near, if not above or below 1%.
Okay,
right.
So close to 1% error rate for 2 qubits. But these are in small systems, so we aren't able to do that same error rate in a 7-qubit system. And then also our best possible readout error is in the around 99 as well.
Sort of the percent level.
Again, at the percent level. So all the pieces can be there. Our initialization is well below 1%. All the pieces are there in isolation. The challenge is to put those all together. Do the engineering optimization to try and get everything as good as possible in a system. So it's really
certainly
a system level.
Sorry.
Yeah. So the recurring challenge is. The recurring challenge is that every time there's an improvement in coherence, you expose new sources of noise. And then you have to diagnose that and try again to achieve coherence limited gates. And it seems to me that the problem is different when you have a sample with 2 or 3 qubits versus a larger sample. There are more interactions to to consider and to turn off. And so these are the things that we're studying.
So, I mean, the context, say, for example, certainly within the US, your major competitor would at this stage be John Martinez's group at Google. They started off with this very simple linear array of qubits, this 9-qubit chip that they've done some stuff with. Now, in the context of the quantum experience, this is not a linear chip. This is a more complex geometry. Can you give me sort of why did you go down this route? Was it just simply the flexibility of being able to do what you wanted to do, or was there a more fundamental design reason why you didn't basically do the same thing that Google did?
So we're specifically aiming towards building a surface code, and the geometry that's there on the quantum experience is intended to be a small section of a surface code. So it's demonstrating some of the technology you would need to start scaling this out to build a square lattice of code qubits with the right connectivity to do your syndrome measurements in between. Mm-hmm. And so actually, we could have with the hardware that's actually in the quantum experience, we could have tuned up additional gates that maybe would have even been useful for certain purposes. But because they don't really help with they don't fit in with this idea that we're moving towards a surface code, we never bothered to tune those up, even though those would nominally be available. So it's really this is our baby steps in the direction of a surface code.
Okay, so getting on to the quantum experience now. So why don't you basically give people who are listening a rundown of what this is and how you guys decided that not only were you going to build a small-scale quantum processor, but that you really were going to open this up on the cloud for people to play around with.
Yeah, so you want?
Sure. Well, I guess maybe I'll speak to the why first. I mean, we think there's, first of all, maybe in no particular order, we'd like to demonstrate that we have high coherence devices that we can control and that we can offer these in a platform that's stable over a long period of time. So this is something this isn't a one-off experiment, but it's something that you can do repeatably and and reliably. We've accepted hundreds of thousands of jobs on the quantum experience from in excess of 30,000 users, and the system's stayed up. It stayed relatively coherent, and
to emphasize, that's been in basically an unattended mode. Like, we spend a lot of time on thinking about the next steps and answering questions and talking to people like you, but our actual day-to-day effort is not keeping the thing running. It basically sits there and calibrates itself, and once in a while it sends us a message.
Excuse me for a moment.
So we'll let this one go through a bit of a break while whatever announcement is happening in IBM is allowed to happen. It's not too surprising. We get the same thing here at Riken.
Sorry about that. We have a Labor Day shutdown.
No problem at all. We get the same thing at Riken all the time.
So, I mean, a reason that I'm very excited about is that this creates an opportunity for everyone, students, everyone, decision makers, researchers, experts, to come in and learn about our system and learn about quantum computing in general. We've seen people consider using this in their classroom. It was the focus of an undergraduate summer program at Waterloo, and so we're very excited about how excited students get about the opportunity to use a real quantum computer with real connectivity and real noise, and to see the effects of that. A third reason that's also important to us is to begin to engage with a community of people and to have a dialogue through the community that's online about directions that they would like to see improvements. to have a discussion about quantum computing. So yeah, and then I guess another point is that we'd like to allow experts access to the technology, so that both for the purpose of you can independently validate what we're saying. You can see the T1 and T2s of these devices. You can run gates. You know the capabilities. It's open, and we also see value in allowing people to experience the actual imperfections in the system.
Yeah, so another way of saying this is that nobody really cares about 5 qubits as a useful device to do quantum computation with. You can simulate that easily. But what's not so simple to simulate is all the imperfections. So there are many spurious modes, there are many different kinds of crosstalks and drifts that if we were to go ahead and use our best possible modeling of how that would behave in order to try and do some kind of really realistic simulation of the device, it's really actually easier just to provide access to the real device, and then people can test their algorithms against the real statistics and the real types of noises that affect these systems.
Sure.
This is also not a device that's been optimized for a particular experiment or a particular algorithm. It's something that is, as Lev said, run in an unattended mode. Yeah, I think. Yeah,
if we were gonna try and publish a paper about some particular algorithm that we were doing here, and we wanted to really get the best possible numbers for a publication, somebody would sit down and spend a week tweaking things just for that, and it would be a little bit fragile, and you'd probably have to do your calibrations and immediately run things and try and get it just right. And we've kind of stepped everything back, put this in a mode where it calibrates itself robustly for kind of all purposes, rather than doing any kind of trade-off in one direction or another. Yeah. And so that's really kind of an honest test of the device.
Yeah, you really get typical behavior from the device.
Yeah, so I mean, it really is a cloud-based platform. So I mean, in the context, so you said now that you've got thousands upon thousands of people, and I mean, obviously, when this thing was first launched and it took off, it got quite a lot of coverage, and I'm sure that a lot of people came into it. As far as I'm aware, in terms of the academic papers, it's still the 4, or has there been more papers that have come out recently using your platform? I'm aware of the initial 4.
So the number I've seen mentioned is 6. I mean, it depends on, some of them maybe you wouldn't call exactly an academic paper, but they're publications that mention the quantum experience. So it's of that order, and we're aware of other work that's not been publicized yet. So it is getting some traction.
So in terms of the vast amount of users that you've obviously had, I mean, one of the interesting things that I'm looking at when it comes to sort of public engagement of this kind of stuff is retention. How many people that, you might get some people who sort of come on, have a bit of a fiddle, then go away. Do you keep track of, how many users are sort of dedicated, that they're really sort of building, whether it's educational programs, research programs, or just spending a lot of time on this thing as sort of part of the community that you're trying to build around the QE?
Yeah, definitely all those statistics are kept. I don't have any particular reason myself to look at them, so I couldn't tell you any of the numbers. But we certainly keep close tabs on how many people are coming back, how many people are doing it just once, how many people make it all the way through the tutorial, how many people have run at least one experiment on the real hardware. All these kinds of statistics, we know those.
I know we have recurring users. People continue to run experiments on the device. They currently are running them.
So I mean, it's definitely just from the rough shape, it's a long tail. There's some people who come in and just see, oh wow, this quantum computing thing is nowhere near as advanced as I thought it was. I thought I could do 3D modeling or financial analysis on it, and they run away. And that's good. They learned something. They heard the hype about quantum computing, and they realized that there's still a ways to go. There are other people who've come in and have realized, wow, this is a way for me to validate my new tomography algorithm or something, and have really sat down and asked for more time, asked for more units to be able to really explore. So we have the whole spectrum.
So in terms of sort of the community engagement, you've tried to sort of build some kind of social media or some kind of forum platform. And you mentioned that this stuff has been taken up by places like Waterloo in order to help sort of in the education sphere. When they did this, especially the Waterloo case, did they coordinate with you guys much, or did they basically build this thing up and sort of say, this is what we've done and we've used your platform to do it?
So in the case of Waterloo, one of our team, Sarah Sheldon, who was previously at Waterloo, went up to make sure everything ran smoothly. We also just made sure that we coordinated insofar as to make sure there was no maintenance going on the machine at the time. Just give them access during the session. And then Sarah was there to answer any questions if they saw particular behavior of the machine. She was able to say, oh yeah, you expect to see that. That's measurement crosstalk that you're seeing, or that's some other effect. But it was pretty minimal. I think it wasn't really strictly necessary that she went there. It was nice for her, and made sure everything went smoothly. But I think it could have been done without that.
Mm-hmm. So I mean, moving on. Certainly, the quantum experience has sort of opened up this idea of allowing, a cloud-based quantum platform, as small as it is at this point. Obviously, it's one of the first, and it's certainly the largest that currently exists in order for people to play around. But in terms of sort of the technology that's moving forward in the context of the US, and the US certainly in superconducting systems. And ion traps, which are the two major leaders, are definitely world leaders. Where do you think you guys are going to be able to head? I mean, there were articles that appeared in the last couple of days in New Scientist and MIT Tech Review about this recent theory paper from the Google guys about quantum supremacy, hitting at about 49 qubits. I imagine, since, as you said, you're positioning yourselves for surface codes and large-scale error correction, that you're going to basically head in the same direction. Is this sort of, especially considering IBM's a private player and Google's a private player, and is this really now turning into a bit of an arms race?
So, I mean, we have plans for larger devices, more than 10 qubits. I guess yeah, I mean, there are plans for sub 20 qubit devices in the relatively near term, and we're looking toward larger systems. As Lev mentioned, we currently have a 7 qubit experiment that's cold, and we're working on that right now. We're in terms of the quantum experience, for example. One direction that's just as important is to add more capability to smaller devices. So improve coherence, improve gate fidelity. Those are not the same thing. Improve readout. Improve our capability to do feedback. And so all of these things are things that you may see on the quantum experience, in the near term.
And then, yeah, we're doing this in a step-by-step way, where there are various challenges that you have to overcome on the way towards a useful device. So one of the near-term challenges that we're going to have to overcome quite soon is breaking the plane. So right now, with all the devices that we've demonstrated here, you can bring in enough connections from the sides that you never actually have to you don't have to access the middle of the code. But obviously, with a decent sized surface code, you're going to be able to have to start coming in from above or below to access the qubits in the interior. And there's a whole set of challenges to do with that in terms of fabrication and microwave mode hygiene and all sorts of problems there. And so we're really just trying to go step by step, make sure we understand everything that's going on at each step, and make sure that we have something that's not a dead end. It's nice to go for 50 qubits all at once, but if you're limited in the coherence there, or you don't really understand that system properly because it's just beyond anything you can simulate, then it's not clear how useful that is to you. So we're just kind of building out with again, an ultimate goal of building a useful surface code based computer, but just solving the challenges as we come along the way. Another challenge that Andrew didn't mention is the cost per qubit. The qubits themselves are relatively cheap; they're lithographically defined, You have hundreds of thousands of dollars worth of room temperature electronics, microwave generators, mixers, arbitrary pulse generators, and so on. And as the number of qubits grows, as we hope they will pretty quickly, you really can't afford to have $50,000 of equipment per qubit. So we have to start working on optimizing the room temperature electronic stack as well. So there's a whole set of challenges that you need to address.
No, that's actually an interesting question in terms of this sort of, I would sort of say, non-quantum aspect of quantum technology. I know that there's certain aspects of the Martinez group that are focusing on this. I know people like Dave Riley and that in Sydney who are spending a large amount of their time looking about how to optimize, signals coming in, signals coming out of the fridge, how I'm going to control all these things at large scale. Obviously, there's that part of it, and there's also the part that you see through the quantum experience, because there seems to be a lot of software engineering, classical software engineering on the back end. Obviously, designing the web interface, designing the forums, collecting the data, all this kind of stuff. So, I mean, in terms of how IBM and you guys at Yorktown are distributing this around sort of the institute, are you now basically pulling in people from other aspects or other areas of IBM who really have not had that much to do with quantum, but are obviously good engineers and good software engineers and can now play a part in this?
Yes, absolutely. So we're looking to the software engineering talent in the building to help us with exactly the kinds of problems that you've mentioned. We also have a large number of engineers who are helping us think about these kinds of problems. A talent that's in the building, and so that's
yeah.
I mean, want to add to that.
Yeah, I mean, this is a research building. We have machine shops and electronic shops and software engineers in the building that have been all through this program been helping out. But as these systems get more and more complex, that we really need them. It's beyond the kind of thing that a scientist or research staff member can spec out themselves. You really need actual engineering analysis done of the right way to set these systems up. And then as we bring in web capabilities, we're actually IBM's a global company. We're bringing in global talent for that part of it.
I mean, do these guys who are not trained in quantum and who are not part of this sort of core research, do they sort of just come in sporadically? They do a little bit and then they go back to their other jobs, or have you really started getting people who have grown up being software engineers who now sort of work on this pretty much full time?
I think there's a spectrum. There are some people who are not quantum people by training and have no specific skill that you would say that makes you a quantum person, but they do electronics for the quantum team. And there are other people with more specialized skills that maybe we don't need them full time to do thermal analysis or whatever it might be, who will come in and answer a question, do a calculation, and I think there's everything in between. But it's certainly, I don't have too much interface with that side of things, but it's clear that there's a lot of people that get brought in for specific issues where they have the ability to help.
So does that happen more so on the experimental guys really coming into this saying, look, we need this kind of software control, we need this kind of stuff to actually work our hardware? Or is this more sort of Andrew getting into your stuff and stuff that I work on a little bit? Is this now, okay, we know that this quantum programming is going to be a thing. So we're going to try and develop this at the much more higher level, even though our hardware is not ready for it yet.
So, I mean, in terms of, I mean, speaking for myself and for what we're thinking about for the quantum experience, I think we're looking, the software that we're going to provide, or the interface we're going to provide, is going to be more of a near-term interface. Something from at the quantum circuit level down, and that's the piece that we're going to focus on. It's closest to the hardware we have, and there's a huge amount of work to do there. But we're interested in thinking about the challenges at that level and higher, and also thinking about the software we need to control that. But for example, right now, I think that given the coherence times we have, and even coherence times you might anticipate in the future, most of the instruction sequence will fit in memory at the moment. So you could pre-compile everything, you could optimize everything, sort of as a unit, and then load this into the hardware and run it. I don't know if you agree.
For the short term, anyway.
Yeah, at least for the near term. And so there's a lot of sophisticated control that has to happen at this lower level. But we can imagine at a quantum program level that we're optimizing circuits, we're acting on circuits. And so there isn't sort of a real-time quantum controller at that level that's emitting instructions down to, from a program, say something like Quipper or Scaffold, down. We can just imagine a quantum circuit and then decompose that, optimize it, work on that, and turn that into an instruction stream for the experiment. So I hope that gives some idea of where we are and what we're thinking in the near term.
But I mean, does this work? I mean, again, I sort of try and reach out now and again to classical engineers and classical computer scientists. I mean, how much is the sort of non-quantum community at IBM really sort of grasped onto this and sort of said, look, there are a lot of things I'm interested, I want to start working on this. But basically I'm saying, how are you engaging the sort of non-quantum side of IBM?
I think it's early at the moment. There's interest, and we obviously, people are aware of what's going on. I think it's a little bit early to be bringing in like whole, for example, compiler teams and tool chain designing and this kind of thing. There will be a time, but I think right now it's a little bit fuzzy even what you would like that to look like. It's probably going to happen at some point fairly soon, but not just yet, I think.
Yeah, but I mean, we have engaged with software engineers in the building who are helping with a lot of the code that I mentioned. So from this circuit level down, the type of software we need to control the experiment, drivers, all this kind of work. There's a huge amount of work to do there, and so we've started to engage people who are experts in that.
So, I mean, does your engagement, do you keep things sort of within the company, or do you guys, I know you're part of the logic program, right? The IARPA logic program?
Yeah.
Is that just basically you guys on your own, or are you collaborating, rather intensely with people like Delft or the other, I suppose the other participants in the logic program are dealing with ion traps, so you're probably not really talking with them much.
So we have subcontractors on that program. So doing, for example, providing some hardware. Yeah, a lot of it's in house. I mean, we have a lot of skills in house. We don't need to go to external sources for very much. Now
that said, though, I think looking forward through the quantum experience, we're hoping to we'll see how this goes, but we're hoping that this can be the beginning of a more open conversation about software and about exactly these kinds of problems that you mentioned, both from at the high level of this software stack down to the hardware. So, the first steps that we're taking in this way, I think you'll see relatively soon. Changes to the interface, trying to agree or have a discussion about the type of interface that needs to be provided to the hardware, things like this, how we build on top of that, what sorts of changes we need to make below that. So I think we're hoping that as we move forward, this will open up a bit.
So, that's an interesting question. Since the quantum experience is quite it's quite an intricate interface, and it's quite a well-built system. Considering this is the first time something like this has really been hooked up to a quantum computer, any type of quantum computer, no matter how big, has there been anything interesting that sort of cropped up? Obviously quantum information and quantum computing's sort of either really heavily physics-based or really heavily theory. It's not so much in systems engineering. Is there anything notable that you can point out that when you started building this, it was sort of, hey, we didn't even think of this?
I think we all underestimated, at least I underestimated, just all the little tricky bits that you need to actually have everything work together, to have something be really reliable so that it can take arbitrary input from a user who maybe is being naive and random, or maybe even being malicious, and have it just work reliably on a system that's been tuned and hacked on by scientists who know exactly what they're doing, and only push the parts of the system that are well tested and work. And so kind of handling all those corner cases and making everything robust took a lot more effort than at least I expected. I'm not sure if that really answers the question.
Yeah, I mean, I guess for researchers, I'm used to writing sort of, you write some one-off code, and only in a few cases have I written something that's really, meant for other people. And this, I mean, it's not so surprising to say that it's quite a lot more work to do that, but the you feel it when you put that much energy into making something like this. And
my brother works in the industry, and it's certainly much different than the kind of code we're used to writing.
The silly things like if the hardware, if there's a problem with communicating with the hardware that causes your experiment not to run one time in 1,000, and then you just need to hit Control-C and try it again. That's not good enough if this thing is running unattended.
So do you know, I mean, I don't know if you guys know off the top of your head, how many, roughly speaking, how many actual runs of the hardware have been executed, not the simulator?
Yes. So, I mean, of the total of the hundreds of thousands of executions, about 10% are to the hardware. The remaining 90 are to the various simulators. And I think a larger proportion is to the idealized simulator at the moment. Yeah. So I think, I'm not sure how to interpret this, but my feeling is that, a lot of people are going into the tutorials and looking through some of these examples and trying things out. And then there is a cost to using the experiment. There's a mechanism, these sort of credits that prevent too much from being put into the queue. And so it could simply be that, but it takes some investment to take something that you're interested in doing and put it into a form that can run on the hardware. Wait for the results. It just takes a bit more work. So, but I think so 10% of hundreds of thousands.
So do you guys take the data? When I run something on the QE, it might be a certain experiment. It's obviously you're logging the circuit I'm running. You're logging the results that are coming from it. Are you guys using that kind of data at the moment?
Not at the level of looking at what circuit you're running. We're looking that you are running circuits and that you're running however many shots you're running, and that maybe you're a heavy user. But we're not looking at not drilling. I mean, I think it is all logged. We could see what circuits you were running and try and scoop you, but we're not doing that.
Maybe I think maybe if you exactly. I think if you're a heavy user, then and you keep needing to request more time, then we probably know who you are. But yeah.
Well, I assume the really heavy users have probably emailed you and asked specifically for heavy use, so you probably already know who they are anyway.
Yeah, and they often have some question about some behavior they see of the system. Is it do we have some insights about it? And usually we can help.
So it's one of the interesting parts about it. Obviously, I'm not an experimentalist, so I'm not used to this. But with a self-maintained system that's been running over hundreds or thousands of executions over, what is it now, 6 months? Have you been seeing any kind of behavior that, like error rates drift or calibration? Obviously you're calibrating this thing quite often. But are you seeing degradation in the qubits? Are you seeing these things possibly breaking?
No,
I don't think so.
No, I mean we didn't really expect to, because we've certainly had experiments called for this length of time with people manually calibrating them and working with them, and we've kept statistics on how things behave over a long run, and we certainly see drifts and occasional times when something seems to go wrong for a day or two, but for unexplained reasons. But nothing that you could sort of just put as like a monotonic decrease in quality or anything like this. It's a little bit of wandering around and occasional times where maybe a calibration gets itself into a bad corner and it does a bad job of does a bad fit to a curve and comes up with a terrible calibration that needs to be either you need to wait for the next calibration, or if we notice it, we'll kick off a manual recal. But no, it's been after the first few days where we hit all the low probability things that only happen one time in 10, but when you run 10 calibrations, you see them. We've actually made it more robust, and after the first few days, it's been pretty much unattended and not really given any surprises.
It's your typical drift.
That's quite optimistic. Then again, I'm not an experimentalist. I'm not sure how these systems are usually behaving over hundreds or thousands of hours of operation.
So, I mean, typically, right, T1, T2 drifts, the gate the bad cases are, I suppose, when the calibration fails for some reason, and you end up with a gate that's far inferior to what you expected. But, otherwise, it's typical fluctuations in coherence. And you can observe this, over time yourself if you were to go online and watch how the coherence changes as the device is recalibrated.
So, I mean, in terms of the future for the QE, I mean, you were talking before about sort of upgrades. Obviously, I imagine IBM is more interested in getting your core technology working. So whether it's the 7-qubit device or a larger device in the future with better coherence. But what point is the QE, is this a secondary thing? Sort of like we build a chip, the chip's really good, we can test it, we can do whatever we want with it. Now we're on to the next generation chip, so that one now goes into the quantum experience.
I don't think we're really thinking that way. I think if we have a good chip that we've used for another purpose and it's been well tested and we know everything about it and it has no surprises, then that would be a good candidate to go in the QE if it has more capabilities than the one that's already there. I don't think it's really that it's a secondary system. It's just that we're probably unlikely to put in an experimental chip that's never been used before into the QE. We want to do some validation first. And if we're going to do some validation and it turns out to be a good one, it's probably going to have actually been used for science before it goes in, just because each cool down takes some time and is expensive, and you're not going to waste that. So, but I don't think it's really a secondary priority. We're kind of committed to putting our best technology in the QE, consistent with it being able to run by itself and be a general purpose device rather than something that's really designed to demonstrate one specific thing.
I mean, I imagine that in terms of the infrastructure, the dilution refrigerator, stuff like that, you probably wouldn't run multiple dill fridges where one's got the 5-qubit chip and one's got the 7-qubit chip. It would be a sort of a replacement thing, just to basically save on resources.
I think both are a possibility.
So we have more than one dilution refrigerator in the building, and it's certainly possible to run more than one experiment in a fridge. So one possible way to extend the quantum experience is to add, as well as a 5-qubit sample running, also maybe a 3-qubit sample with better coherence or with different capabilities, like maybe feedback or something like this. So these are the kinds of directions we might go. Nothing is set in stone at the moment, but yeah, there'll always be something running, and it doesn't have to be limited by fridge resources.
Sure. So in terms of your users, I mean, what's been the most requested thing? I mean, so the quantum experience that you guys released was kind of ideal for me because it put everything in the language that I'm used to and everything in the language that I worked with. With other people, not so much. So in terms of people playing around with it, or more specifically the research community, what's sort of been the number-one thing that people have come back at you and said, look, guys, can you do this?
I'd say that's probably gone.
Okay. I mean, so we've had for our own interest, we're looking at allowing arbitrary single qubit rotations, not just a discrete set. And that should allow you to write more compact circuits. We've heard requests for adding classical registers, the ability to make repeated measurements or apply feedback from those measurements.
Right.
I think those are the main. Were there a few other requests?
I think a more programmatic interface, so that you don't have to do so much by dragging boxes around on a GUI. which we've implemented to a certain extent. I don't know if you've seen recently. We have a beta feature where you can actually write in textual programs, and they can.
Well, I saw that paper from this woman who appears to be a climate scientist down in the South Pole who did this.
Yeah.
That was certainly an interesting thing to pop up.
Yeah, so I think that was based on that in the South Pole you don't get much internet connectivity, and so she wanted something that she was able to run offline locally and test her programs. And then when she had her precious internet connectivity, to actually use the system as efficiently as possible. And so she basically reverse engineered our language for doing quantum computing, our quantum assembler Quasm. So she basically wrote an independent implementation of a simulator for that.
I mean, did she talk to you guys much? I mean, what was her motivation? It seemed way out of left field from what I can tell is a sort of day job.
As far as I know, the most wonderful motivation, curiosity. I think that's. Right. I think that's. Yeah.
I think she was limited. You know, she's obviously got a lot of skills. She was stuck in the South Pole with nothing much to do at the South Pole, I guess. You know, she saw this tool and realized that actually she could play with it even more if she had better bandwidth to it. So she wrote her own implementation of the simulator. Yeah,
I thought it was great.
So, I mean, this is related to what Lev said. Another feature request is, it gets it's a lot of work to write down a circuit and decompose it into all of its basic gates and then put it into the quantum experience. So we're trying to allow, we plan to allow a more modular description of the circuit. These are kind of obvious things, but batching gates together, defining new collections of gates. So it would allow you to, so for example, if you wanted to implement a small adder or a small bit flip code, and you need a Toffoli gate, this will be convenient. It'll also let you very quickly run into the coherence limit on how many gates you apply. Yeah.
So you mentioned earlier on, Lev, that IBM's focus is obviously on the surface code and scaling up in the context of that error-corrected model. With most of the major labs and most of the major groups, they sort of have the main focus, which is obviously a scalable digital error-corrected quantum computer. But then they sort of have the side projects. So I know both, obviously, Google and Sydney and a few others, even here in Japan, looking at this quantum annealing route or things like boson sampling or sort of other side technologies that, for various reasons, whether you agree with them or not, may be faster to achieve. Are you guys doing similar things at IBM, or is it really, narrow focus? We want to hit this large-scale digital error-corrected machine.
So we certainly are focused on things that will allow us to progress towards a large-scale error-corrected machine. But along the way, we're hoping that we'll be able to do something useful before we build such a machine, because that's really still a ways off. And so our big sort of short-term goal is quantum chemistry. So we're looking towards different ways of using small quantum computers without full error correction to do calculations in quantum chemistry.
So I ask most people who come on this podcast is to give me sort of a prediction of where you think the field in general, and specifically your own hardware, will be in the next 5 or 10 years. You guys want to give it a shot as to where you think you can get to by 2020 or 2025?
So being optimistic, I think we would on the surface code path towards that direction. I would hope that in 5 years we would have 2 logical qubits that we could do interesting things with. So,
2 logical qubits in 5 years.
Yeah, I think that's a optimistic but potentially doable goal. I think at that point you're gonna learn a lot about along that path. You're gonna learn a lot about the challenges of doing logical qubits, and it's not gonna be easy. And I think I can't see beyond that because I think there's so many unknowns up to that point. But I think at least to there, I think that's something we should be aiming for. And then I hope also we'll have something that can do small quantum chemistry problems. Although I'm not confident in 5 years whether we can do anything that couldn't already be done with a supercomputer and lots of sophisticated couple cluster or whatever algorithms. But you never know. I don't know if you have an opinion.
No, I think the most important challenge, and I think everyone in the community is well aware of it, is to think what to do with a small machine. Particularly one where you don't have error correction, and you need to have new techniques for mitigating that noise in some way to to compute the observable that you'd like to see. And I think that we'll probably see machines that are approaching that size where we can start to start to observe things that we can't predict through simulation. And I think that would be very interesting.
Okay, so we're running up to 50 minutes, which is usually the maximum that I like to run these things before people basically start glazing over. So just to finalize things, is there anything you guys want to plug, anything interesting in terms of programs running at IBM, opportunities, or just stuff you think is pretty cool that's going to come out in the next week or month or so?
I think we definitely want to point people to the quantum experience. So if they go to ibm.com/quantum computing, they can try what we've been discussing. So
yeah, and
like
just make sure everyone listening realizes there's something for everybody in there. There's tutorials for people who don't know any quantum computing. There's the ability to run on a real quantum computer and test your ideas if you're an expert. And there's a community where you can discuss next steps and problems and challenges. So I think we'd really like as many people as possible to check it out.
Yeah, and I certainly can encourage people to do it as well. I thought it was a great bit of fun when I was playing around with it a few months ago. Obviously, there'll be links in the low bar, both on YouTube and all of our accounts, pointing people in that direction. So finally, both of you, thanks again for sitting down with me for an hour and giving a bit of a rundown of what's going on now at IBM. So both Andrew and Lev, thanks again.
Thanks very much.
Thank you.
Great. So everyone, thank you again for joining in. For those of you who watch live or download later, I always say, please subscribe to us on our various accounts. The number of downloads and listens that we're getting to now is actually quite large, and I'm very, very appreciative of everyone who's managed to make this podcast a little bit more of a success than I thought. Our next episode, we haven't locked in a guest yet. There are a few people that I'm still nailing down times for. But of course, check out our Twitter feed and our YouTube account. As soon as we have our next one scheduled, I'll let you all know. So thanks a lot again. Cheers.
Bye.